All right, hello. We're just looking at a yellow piece of paper right now, but I'm about to write on it, and I'm going to go over problem 220. Let's see, 220 in the book. Okay, it's on page 63, and I'm just going to help you get it started. Okay, what we have is a pipe. I'm not going to talk about too many specifics about the pipe, but one thing I'm going to say is going into the pipe there's a certain amount of energy. Okay, and it says the energy, and we're going to call that E inlet, going into the pipe is 75 feet. Now you're not used to seeing feet as a unit of energy, but we do treat it like energy, like potential energy. And ultimately, at the end of this problem, you're going to have to convert that to horsepower. I'm not going to go over that here, but you're going to need to do that. Okay. So E outlet is what we're going to be solving for. Okay. What they've told us is the amount of energy going in to the water being pumped into it, 75 feet of total head, total energy. Coming out, we're going to figure that out because that's going to tell us what the loss is. But they did tell us a few things about coming out of the pipe. They said, number one, the velocity that's coming out of there is 5 feet per second. Okay, make sure you can see that. Yeah, it's not doing so good. So the velocity at the outlet equals 5 feet per second, and the pressure at the outlet is equal to 12 psi. All right. So what is this energy thing? And we've talked about it a little bit, but Bernoulli's equation defines what the total energy in a system is. Okay, and I said it's v squared over 2g, which is velocity squared over 2g. This is a kinetic energy term. So we'll say this is kinetic. And then it has a pressure energy term, which we're going to call P over gamma. So the pressure divided by gamma. And you'll notice this is pounds per square foot divided by pounds per cubic foot. That'll give you feet. This will give you feet too. Or a unit of length, which is really a height measurement, which is a way to express energy. And then a third one, and this we'll call this pressure energy, kinetic energy, pressure energy, and then we'll call this last one Y. This is just going to be a potential energy. All right, so kinetic energy, pressure energy, and potential energy. Okay. So we know it's 75 feet going in. If you add all these things up to what's going on inside, the kinetic plus the pressure plus the potential energy going in is 75 feet. How do we know that? I don't know. We just do. Okay. They're asking how much is lost as it goes through the pipe. And how would it lose energy? Well, it could lose it in a number of different ways. It could lose it if it's at a different height. I depicted this thing as being flat, but it's not necessarily. And we don't know the pressure going in, and we don't know the velocity going in. There's also friction or losses that happen within a pipe. So they did give it a length of this pipe. It was pretty long, 1,200 feet long. So there's plenty of opportunity for friction losses as it goes through the pipe. So ultimately we need to find E outlet. Okay, and it gives us the velocity in feet per second, and it gives us the pressure in psi. So I'm thinking we probably want to get rid of the I. We want to get rid of the inches and change it to feet. We know gravity is 32.2 feet per second squared, so that's feet, and everything else is in feet in seconds. So let's go ahead and convert the pressure. And I know you guys can do this, but I'm just going to do it real quick. 1728 pounds per foot squared. So E outlet is going to equal to the velocity, 5 feet per second. that whole thing squared, divided by 32.2 feet per second squared. So you'll notice you'll end up with a foot on top because you have feet squared over second squared and then feet over second squared. So that's good. And then we've got the pressure, which we converted to 1728 pounds per foot squared, divided by unit weight of water, pounds per foot cubed. Okay, so that is our pressure term, our pressure energy, kinetic energy, pressure energy, and now potential energy. And it tells us that at the end of this, at the outlet, the height of this thing is 10 feet above a datum. Okay, so I didn't give myself much room to show that, but we'll say this is the datum here, whatever we're measuring from, and this here we said is 10 feet. Hopefully you can see that okay. So then you just add 10 feet, and the units work out. Okay, so this is the energy in the outlet. If we subtract that from the energy in the inlet, we know how much was lost, and then we have to convert it to horsepower. That is your task. So that should help you get going on problem 220.